Welcome for this video about sets. Today we are going to split the video in two because there are many definitions. The first part of the video is going to be about these definitions. So we have six symbols. One, the union. This is intersection, the complement of A, the difference, the Cartesian product, and the symmetric difference. Then we have a vocabulary of subset and superset, and also some symbols which come with them. We have a definition, which is the Powerset, and the Disjoint sets. We are going to learn also two new formulas which can sometimes be useful for exercises. In the second part, we are going to discuss some number sets, natural numbers, the integers, and the rational numbers. Then we are going to learn two formulas which actually can be summarized into one such formula. It's for counting the numbers of elements in a set. It's called in German Formel, in English inclusion-exclusion principle. The first thing to remember is the definition of a power set, and it's a set of all possible subsets of the set, including the empty set and the set itself. Subset is Teilmenge in German. So how do you note it? You write it P of A. That's the power set of A. What is a subset and what is a superset? Subset is called Teilmenge in German, and superset is called Obermenge in German. And A here is kinda smaller than B. So it's just to remember. So A is a subset of B, and B is a superset of A. And that means that when you have an element, if this is an element of A, then it's also an element of B. Now, what can you say about A and B if you know that they are disjoint? On this theme, A and B are disjoint. So what you can say, and that is the answer of this question, is A intersection B are the empty set, because there is nothing in between. And here, in an example where A and B are not disjoint, there is something in between. So A intersection B is not the empty set. Now I have a good news for you, and the good news is you can recycle the formulas you learned from logic and use them for the sets. So yesterday we saw three formulas: the law from De Morgan, the distributive law, and the application removing law. If you don't remember them, watch the video logic again. How is it that we can use these formulas for the sets? Because these symbols are the same. The end of logic is the same as the intersection of sets. The OR of logic is the same as the union of sets. And the not is the same as the complement. The complement, you can write it also not A, the complement of X and A, or X difference A, which is everything outside of A. There are two new formulas which can be useful sometimes, but we are not going to use them today. So A subset of B is the same as this. How can we kinda understand it? We look at this. A is a subset of B. And now we look at A and B. So what is in A and in B is actually A. And what is in A or in B is B. This is for this part. Now, how can we understand this part? It's a bit trickier, but not that difficult. So if you look at what is not in B, you see this yellow thing. Now, if you look at what is not in A, it's actually the yellow thing and the purple thing. You can see that not A is a bit bigger than not B. Therefore, not B is included in A. What I just said is not a mathematical way to write it down, but it's good to understand. Just as a remark, surface equality and difference removing law are not the official terms, but it's better to put a name on something so that you can remember it. So A difference B is the same as A and not B. And we can understanding on the scheme. So A difference B is A without B, so it's here. And it's also A and not B. Now let's practice. Pause the video and see you for the answers. I hope you did the exercises. Now we are going to correct them. The answers. So the union is what is in M or in N. Of course, since it's a set, we don't cut the same element multiple times. So the 2 is only one time here. The intersection is what is in M and in N. So it's actually only 2. the difference is in M, but not in N. So it's only 0 and 1. The symmetric difference, it's easier to understand it when you look at the scheme. It's what is in M or in N, but not in M and N. So not here. So it's 0, 1, not 2, not 2, 3, 4, 5. Here you go. The Cartesian product, it's easy, but it's a bit long to write. What I do is I write 0, 1, 2 here, and here I write n, so 2, 3, 4, 5 here. And I just write the tuples, so 0, 2, 0, 4, 3, 0, 4, 0, 5, etc. And after that, I write it properly, and that's it for the Cartesian product. Now, more interesting, the power set Pn of n. So here is n, and what is a power set? It's a set of all subsets of n. So we count what is the subset without elements is the empty set. What are the subsets with one element? 2, 3, 4, and 5. Now with two elements, 2 and 3, 2 and 4, 2 and 5, 3 and 4, and 4 and 5. These are there. Now the subset with three elements, 2, 3, 4, 3, 4, 5, etc. A way to not forget them is I write somehow 2, 3, 4, and I look, okay, I put nothing here, now I'm gonna put something here, like that. There are many ways to understand it. And now n, because it's only subset of n with 4 elements. Don't forget the empty set and the set itself. Now how to check that you have the right number of elements? You do 2 to the power of the number of elements in your set. So here we have 1, 2, 3, 4 elements. So we do 2 to the power of 4, that's 16. Therefore here there should be 16 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Here we go. It's likely to be true. Now for the second exercise, we want to find epsilon. So we look at it and we see, oh, there's a lot of knot. It's not cool. Let's put a big knot so that maybe it will remove the knot. And here I remove knot A and B. I recognize the first one from the Morgan. Knot A and B is same as knot A or not B. Knot A and B is same as knot A or not B. So not becomes the original set. So here you go. Here you go. And now here I see I have this symbol, the same symbol here inside the parentheses, and outside the parentheses I have this symbol. So I think about the distributive law. Because here you see I have this symbol on the right. Like that. I would call it the reverse distributive law because I'm going from right to left. And I use it, and I get this one. And here I see it does not depend on A because it's true whether I have A or not A. So it doesn't matter. A doesn't matter. So I remove A, and I'm left with epsilon is the same as B. Now let's go for the second part, what we have to remember. So there are the number sets, natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. We have integers, which are natural numbers and their counterpart, which are negatives, plus the 0. And now we have the rational numbers, fractions of integers. Just to put the name of German, natürliche Zahlen, ganze Zahlen, rationale Zahlen. Now we are going to see formulas how to count the numbers of elements, and this is the important part of today's video because it's actually the one part that you can easily find back, and it's a useful formula for the exercise. So let's start it with an easy example. So here we want to know what this is, A or B, and this part is to count the elements. So I want to count the number of elements in A or B. And what I do is I'm just counting A, the elements in A, and the elements in B. But then I counted this part twice, right? So I'm gonna remove it once, and now I have a number of elements in A or B. Okay? How does it look like when I have 3 sets? So A or B or C. It's the same idea. I add each set, A plus B plus C, and I remove the things which are in between. So A and B, A and C, and B and C. But now I remove this part in the middle too much. So I add it. And here you go. You have what we call the ZIP-Formel in German, or the inclusion-exclusion principle in English. Okay, now time to practice. This example I modified from a website, so if you want the original reference, you can look in the description. Among 100 patients admitted to a hospital, 45 are diagnosed with malaria, 30 with stroke, 20 with pneumonia, 6 have malaria and stroke, 1 has malaria and pneumonia, 5 have stroke and pneumonia, 1 has the 3 diseases. What is the percentage of patients with none of these 3 diseases? Here you go. Pause the video and answer the question. I hope you did it. And now let's go for the answers. Here I made a scheme. I wrote in B all that we had as informations, and what I put in purple is what I added after that. So we start with the information of 20 with malaria, here 20. 6 have malaria and stroke, so I know malaria and stroke is 6, malaria and pneumonia is 1, stroke and pneumonia is 5. Okay. Now I know that 1 has the 3 diseases, so I put a 1 here. Okay. Now I know this is 6, so minus 1 is 5. This is 5, so minus 1 is 4. And now this is 1, so minus 1 is 0. Okay. Now I know that this whole thing is 30, and I have those informations there, so I put 20 here. Now I knew this, and I knew 20, so I do 20 minus this, and this is 15. And the same here. And now I have my whole scheme ready for the answers. And for that I use the formula we just saw, and I will paste all the informations. And like that I know that this whole thing is 48 patients. Okay? And now I know in total we have 100 patients. So I do 100 minus 84, and I get that 16% of the patients have none of the diseases. That's it for this video. See you tomorrow at 7 AM for the next video about sums and products.